Over the last week or so, we've looked at electric fields surrounding charged objects that produce non-uniform fields. The first one we looked at was the electric field surrounding a positive producer. That's a non-uniform field. These field lines are not parallel to each other, which means that the field changes depending upon what location you're at. That means it's a non-uniform field. The second field that we looked at was surrounding a negatively charged producer. It moves, or it acts toward the producer. It's non-uniform as well. These field lines are also not parallel, which means the strength of the field varies depending upon what location you're at. Both of these fields can be described by the producer equation. The producer equation that we learned last week, E is equal to KQ over R squared. Now, both of those fields can also be expressed using the experiencer equation, E is equal to F over Q, if we have an experiencer in the field. So if we have a little positively charged particle or a little negatively charged particle in that field, we can use information about that experiencer to find the value of that non-uniform field as well. So two equations that apply here. There's the producer equation if we have information about what's causing this non-uniform field, and the experiencer equation if we have information about what's experiencing this non-uniform electric field. We're going to introduce a third field here now. The third field is the field that exists between these two charged parallel plates. We talked about this on Friday. Let's make the top plate positive, and we'll make the bottom plate negative. The electric field that acts within this situation here goes from positive to negative. And these field lines, you'll notice, are parallel to each other. That tells us that this field is a uniform electric field. The density is constant. The strength of the electric field is constant no matter where we are in between the fields. Introduce a little positive right here, or a little negative right here, or a little positive here, or a negative here. It doesn't matter. The field strength is going to be the same no matter what. Now, that second equation that we learned here, E is equal to F over Q, is still absolutely valid for this uniform field as well. But we have to have information about what experiences the field. The equation that's not valid is the first one, E is equal to KQ over R squared, because that's only valid for a non-uniform field. The good news is we learned another one on Friday that's valid for a uniform field. This equation, E is equal to delta V over delta D. What does delta D stand for there? Yep. Good, it's the distance between the plates. It is not, contrary to what a lot of people will put on a test if given this information, it's not the distance from the top plate to the positive charge, or from the bottom plate to the negative charge, or from the bottom plate to the positive charge, or it's not how far the negative or the positive particle has moved. None of that stuff. It is quite simply the distance from the top plate to the bottom plate, independent of what charge is present inside that field or where that charge is. The distance between the top plate and the bottom plate. Delta V, on the other hand, is what we call the potential difference. The difference in energy per coulomb of charge between the top plate and the bottom plate. It's analogous to, remember we said on Friday, we go down to 7-Eleven with $10, each of us. The money per person when we go into 7-Eleven is $10. The money per person when we come out of 7-Eleven is $8. The difference in money per person is $2. The potential difference is analogous to the difference in money per person. It's the difference in energy per coulomb of charge. You got a certain amount of energy per coulomb of charge up here. You got a certain amount of energy per coulomb of charge down here. The difference in energy per coulomb of charge between those two spots is the potential difference. We'll talk more about potential difference later this week. I just want you to have a basic grasp as to what it means right now so that we can do these problems. Now, I often draw a little Venn diagram within these equations as well, within these electric field equations. Those top equations always represent when we have a non-uniform field. And those bottom two equations always represent when we have a uniform field. What's the deal with that middle equation? That middle equation that appears to be in both. It's the experiencer equation, and it can be used in either a uniform or a non-uniform field. As long as you have information about what's experiencing the field, you're allowed to use that, regardless of what kind of field you have. So if you ever find yourself with this, use one of the first two. With this one, use one of the first two. If you ever find yourself in this situation, use one of the last two. Let's take a look at an example that we have on page 568. Let's read through this. And first of all, after we read through it, let's determine what's not really important to this question, what's not really relevant to the question. Somebody at the end of last class was asking me, like, what kind of stuff can we expect to see on tests? Well, this is a relatively straightforward question, but it's this kind of idea that you see on tests, right? Where you have context. You see something about a cathode ray tube that you've never heard of before, or see something about some other kind of technological application that you've never heard of before. Don't sweat that. We'll read through this and we'll identify what's not important and how it boils down to a pretty simple, straightforward question. It says a cathode ray tube computer monitor accelerates the electrons between two charged parallel plates. These electrons are then directed toward the screen to create an image. The plates are this far apart and they have a potential difference of 25,000 volts between them. What's the magnitude of the electric field between the plates? Tell me something in this question that's not relevant to the question. What can I cross out and not change the question at all? What can I cross out and not make this question any harder? In fact, what can I cross out and make this question easier? Dylan, what's one thing? Okay, the electrons are directed toward the screen. I can get rid of that because that doesn't make any difference in the solution to this problem, right? What else? Yeah. It's a cathode ray tube. What's a cathode ray tube? Well, they describe for us what a cathode ray tube is, but we've never heard of it before, right? So it's probably not going to be relevant to the question. There's no numbers up there, certainly, and there doesn't seem to be any physics up there. It's just a bunch of words that are kind of providing context. We don't need the context. We need the content. We need the content of the question, which is, here's the distance between the plates. Here's the potential difference between the plates. We're looking for the electric field strength. That's the kind of thing we see, right? The kind of thing where we're given a bunch of information, but only a little bit of it matters. All right. Do we have a uniform or a non-uniform field here? The diagram itself helps us a lot with that. Uniform or non-uniform, Jared? It's uniform. Look at that diagram. The field lines are parallel to each other. Now, given what we have given to us, we could probably make that assumption anyways. It's probably a pretty safe assumption. But when we see that diagram with parallel field lines, okay, we can be positive that it's a uniform field. And if we have a uniform field, we're allowed to use the last two equations, F over Q, delta V over delta D. Which one fits the givens the best? That's what it comes down to at this point, right? Not which one's a better equation, which one fits the givens the best. Which one is it? Delta V over delta D. Justina? A non-uniform field would have field lines that aren't parallel to each other. So field lines that are, those first two diagrams that we drew up on the board here, these are non-uniform fields because those field lines aren't parallel to each other. They'll eventually intersect if we keep drawing them further for long enough. Make sense? Parallel field lines, uniform field, last two equations. Non-parallel field lines, first two equations, non-uniform field. All right, it's a pretty straightforward question at this point. Delta V over delta D, we get 25,000 volts, or 2.5 times 10 to the 4 volts, divided by my distance of 1.2 times 10 to the minus 2 meters. And I think when we do the math there, if I remember right, it was 2.1 times 10 to the 6. Is that right? 2.1 times 10 to the 6. What units did we use for electric field in all the problems we did last week? Newtons per coulomb. Is that still valid? Sure it is. Even though we're dealing with another equation, it's still perfectly valid. But 2.1 times 10 to the 6 newtons per coulomb is exactly the same thing as 2.1 times 10 to the 6 V over M, volts per meter. So it doesn't matter which one you use. They're both correct. The one that probably makes the most sense in this question is the volts per meter because that's the equation we used. But if you put newtons per coulomb, that would be correct as well. Just be prepared to recognize both sets of units. I'll give you a few minutes to work on these ones. They should go pretty quickly for us, but work on them in class here for a few minutes. Let me know how you find them. If we need to go over them, we will. If not, then we'll move on to the next thing. All right, it doesn't seem like anybody's having too much trouble with these on 568. I'm going to assign a little bit of homework here for you now. The questions that I'd like you to do for homework are check and reflect on page 569. I don't want you to do all of these here, not yet, at least. The questions that I'd like you to do are question number 2, 4, 6, 7, 9, and 10. A number of the other ones you will eventually have to do, but right now they're not going to make a lot of sense to you. So hold off on doing the other ones right now, okay? 2, 4, 6, 7, 9, and 10.